bit about maybe something that you can solve. My favorite theorem in combinatorics is Graham-Pollack theorem, which says that if you take a complete graph on n vertices and you try to partition its edge set into the edges of bicliques, a biclique is a complete bipartite subgraph, then you need at least n minus one such bicliques. It's known that you can do it with n minus one. There are some small, in the picture over there, you can see two partitions for K4. One is in stars, like the red star K13, the blue one K12, and the green one. Or you can do it with a K22 in the picture on the right, and then two edges, the blue and the green. For some people, this theorem, so it doesn't have a combinatorial proof. All the proofs are linear algebraic. And some people are searching for such a proof. But if you read, a preface to a famous book, there are some people who actually are happy when combinatorial results do not have combinatorial proofs. And I know at least one of them. And I'm also, I also am happy if this theorem doesn't have a combinatorial proof. So anyway, this is a very nice result due to Graham and Pollack in the 70s. It has a geometric kind of application, and this goes back to the work of Sachs in the late 70s, who studied families of k-neighborly polytopes. So if you restrict yourself to d-dimensional standard boxes, so the edges of the boxes are parallel with the axis, and so you have this notion of k-neighborly boxes, and you're interested in calculating the maximum size of such a family. And Sachs observed that the Graham-Pollack theorem implies that this parameter n1d actually equals d plus 1, and you have an example there of boxes in R2. You have 3 boxes. That's a maximum you can find. Later on, Noga Alon obtained a more general result about nkd, which is the largest n, such that the complete graph on n vertices can be covered by d bicliques, such that each edge is covered at least one, so it's a cover, and it's at most k times. So when you restrict to n1d, that's exactly a biclique partition, and that will give you d plus 1. The interesting thing is that this parameter, for when you do this type of coverings, where you can cover an edge more than once, the minimum number is not known. So Alon, in his paper in 97, introduced this parameter BPT of Kn, which is the minimum number of bicliques that cover the edges of Kn, such that each edge is covered at least once and at most t times. And of course, t equals 1, it's what Graham and Pollack study, and that for the t equals 1, you get n minus 1. And sorry for the typo here, but when t, in general, for general t, this parameter alone proved that it behaves like a square root of order t of n. And even for t equals 2, so Huang and Surakov, they have a very nice paper in 2012 in which they disprove a conjecture called Alon-Sachs-Seymour conjecture, also involving biclique partition. But they also give slightly better bounds than Alon, lower bounds. And so they prove that this BP2Kn is at least square root of n. This is also linear algebraic, so all the lower bounds are linear algebraic. And Alon construction from 97 gives 2 square root of n. So this point for general n, nobody knows like what does this parameter behave like. Is it 2 root n? Is it root n? I don't know, something in between. It's not known. So yeah. Okay, so now coming back to the topic of the talk, the flip graphs. So there are many flip graphs in the literature. So kind of we start with the more delicious ones, the pancake ones. So in the pancake graph, you have this problem goes back to Jacob Goodman in American Math Monthly in 1975, where he posed this problem. What's the minimum number of flips that you can sort a stack of pancakes? So in order to sort the pancakes, you need to bring the stack of pancakes to this shape on the left, where you have the sizes of the pancakes in decreasing order as you go from the bottom up. And all you can do is when you sort them, you put your spatula under a substack and you flip it. Okay. Now you can this situation. You can represent the pancakes as permutations, and basically every flip corresponds to a prefix reversal. And so there's been a lot of interest into the diameter of this graph. So I give you a picture there on the right of the graph when n equals 4. And this is the paper that Bill Gates wrote while he was an undergraduate at Harvard with Papadimitriou. And in the red, in the inequalities there, I put the bounds that they obtained. They obtained an upper bound of 5n plus 5 over 3 and 17n over 16. And those were later improved slightly. So the lower bound was improved by Hedari and Sudborough to 15n over 14. And the upper bound was improved by this long list of authors in 2009. But again, for general n, the value is not known for this diameter of the pancake graph. Now, as I mentioned earlier, the pancake graph is a Cayley graph of the symmetric group of n-elements with n-1 generators, and I kind of listed them there. It's the transposition 1, 2, or the transposition 1, 3, where you flip the first 3 position, and the one on position 2 stays the same, or you flip 1 with 4 and 2 with 3, and so on. And the last one, it's kind of like 1 with n, 2 with n-1, and it depends on the parity of n what you do in the middle there. And so it's clear that the largest eigenvalue of the adjacency matrix is n-1. And Sessi in 2009, using representation theory of the symmetric group, proved that the second eigenvalue is n-2. And this was also proved in a kind of more general form by Fan Chung and Josh Tobin in 2017. In the sense of a more general result is that they look at Cayley graphs with n-1 generators, which for every j which is greater than 2, flip 1 with j. And whatever in the middle, you fix some kind of permutations, and in the middle, in the positions 2, 3 up to j-1, you can do other things, not just flip them. So they prove for this family of graphs that essentially the spectral gap is 1 for the pancake. Now, of course, now you're familiar with pancakes, so you can do burnt pancakes. So in the burnt pancake version, each pancake has 2 sides, the burnt side and the non-burnt side. And when you want to sort them, for example, you want them from whatever, your kids put the pancakes in some stack, in some weird order, and you want to bring them to the stack where, again, it's decreasing in the size from bottom going up, but also all the burnt sides are at the bottom. Okay, so you can model this in terms of instead of using permutation, you use Sine permutation. So so the vertices are going to be more here. So they're going to be, you can model your situations by having a +-1, +-2, and so on, +-n. And when you flip, you see like you do a prefix reversal, but you also change the signs. Okay, so there are some partial pictures of this graph. So this is a bigger graph than the previous one because you don't have just n factorial, you have 2 to the n times n factorial vertices here. And you can look again for the thing that is more kind of known about these graphs, or like kind of more famous problem about it, is the diameter. And the best bounds for this problem are due to Cohen and Bloom, and there's an upper bound of 2n-2, and there's a lower bound of 3n/2. The upper bound of 2n is not so difficult to imagine, because you can always, the idea would be to bring the largest pancake that hasn't been sorted, you bring it to the top, and then you flip it. So you can kind of do 2 moves of that. But to do something better, it's quite ingenious and so on. So again, this Cohen is also kind of Hollywood famous. He's involved, like wrote some, so he was an undergraduate, I think, at Harvard and did a master at Berkeley. And then started writing for, I think, Beavis and Butthead or like some other TV shows, Simpsons, and he created Futurama. So that's David S. Cohen in the paper, and later on changed his name to David X. Cohen. Okay. Now, the ones that I advertise on the title are the flipped graphs on the perfect matchings. So here you take all the 2n minus 1 double factorial perfect matchings of k to n, and you make two adjacent if you take two edges and you just replacing by two other another matching on two edges on those four vertices. So this graph has been studied by many people. So Diaconis and Holmes, they know this connection with phylogenetic trees, and they were interested in random walks on these graphs, which they can use to generate perfect matchings at random. And they proved some strong results. So they used representation theory to prove some strong results on this, how many steps it takes to have like this cutoff phenomenon, approaching the distribution on the perfect matchings, approaching the uniform distribution in this kind of total variation distance and so on. Hernando, Hurtado, and Noy studied these graphs, but for geometric perfect matching. So here you have two endpoints in kind of general position, and you only look at perfect matchings that do not cross, and the number of those is actually Catalan number, but the edges are defined the same way. So that's a kind of more combinatorial problem. And then there is this paper that was basically kind of our motivation. There's a very nice paper by Fabila Monroy, Flores Penaloza, Wemer, Hurtado, Urrutia, and Wood in 2009, in which they studied the chromatic number of several flip graphs. I'll mention the results in a little bit, but now in the picture, the graph there is the one for MK6. So you have 15 perfect matchings, and the degree is 6. So this is MK6. It's a picture taken from the paper of these 6 authors. Okay. Now, this graph is also part of this perfect matching association scheme, which has been studied in the context of Erdos-Corrado theorems by several authors. So Chris Gotzel and Karen Marr, they have a paper and a book in which they have such result. Srinivasan has a paper, Ku and Wong, and Nathan Lindsay. We mentioned one of his papers in our preprint, but we didn't mention the kind of the closer related ones. So, but yeah, thanks Nathan for letting us know. Now, so these authors, they study chromatic number, and they made this, it's a simple observation that if you take the same graph on the complete bipartite, so if you take all the perfect matchings of a complete bipartite graph K and N, and you make two adjacent if they differ by an edge flip, then the chromatic number, this graph is bipartite. Because on the complete bipartite K and N, a perfect matching is essentially a permutation, and an edge flip, like a flip of two edges, is just a transposition. So using this result and some clever combinatorial arguments, they prove an upper bound of 4n minus 4. But they did the calculation. So for n equals 2, the graph is just complete graph on 3 vertices, K3. For n equals 3, the graph is the one that in the picture, and you can actually, with a little bit of, if you dig a little bit deeper, you can notice this graph is actually a Kneser graph. I think it's Kneser K62, something like. It's a strongly regular graph with 15 vertices and degree 6. And the chromatic number is gonna be 4. And then by computer for n equals 4, so when n equals 4, the graph has 105 vertices, and it's 12 regular, they observe that the chromatic number is 5. So, the pattern is kind of clear. So they conjecture that the chromatic number is n plus 1 for any n. Now, this is what I tell you is a joint work with Gordon Royal and Zhao Quang Tan. Now, that's me on the left. That's not Gordon Royal, that's Noga alone. And the one next to him is Brendan Gilbert, who is an undergraduate student of mine and co-author with me and Noga Alon and Brenda Mackay and Jack Cullen on on a paper on addressing of graphs. And Zhao Quang Tan is on the right. He's visited me in Delaware for 6 months. He's an undergraduate student from Singapore working with Chenku. So the reason we're so happy there is that on the blackboard, we told Noga about all the problems that we studied, these problems about, you see like on the right, you can see like the flip graphs and so on. And Noga couldn't solve the problems on the spot. So if you've, talked with Noga alone about problems before, and that's a good sign. So we were quite happy that, at least the problems that we're talking about were, Noga couldn't solve them in 5 minutes or 10 minutes. Okay. So the first thing, one result we did is to improve the upper bound. And the idea here for, that's the proof and so on, and where you can get basically the upper bound cut in half. Like the way this bound comes about is if you know the coloring for, there's a very nice coloring for Johnson graphs. So Johnson graphs, the vertices are subsets of a fixed size of a set with n elements, and two of them are adjacent if they differ in exactly one element. And there's a coloring, I think, which is due to, again, to Ron Graham and Neil Sloan, in which it's a coloring with n colors, where n is the size of the ground set, in which you color a subset by the sum of its entries modulo n. So that's in some sense what we did here, but so we just had to live in a nice field. So we just take Q, the smallest prime power that's at least 2n plus 1, and then you take any injective function, you put your vertices 1 to n into this field FQ. And if you have a perfect matching x1, x2 all the way to x to n minus 1, x to n, you color it by this function. And it's a fairly simple argument to show that if x and y are adjacent, so if x and y are adjacent, they will differ only in two edges. So, for y, x1, x2 will be the same, x3, x4 will be the same. It's only in two edges, let's say at the end, that they will be different. And when you write down the difference between fx minus fy, this will be a product of two non-zero entries in the field, so it has to be non-zero. So that's how we get this upper bound, and then some number theory tells us that this smallest prime power, that's at least 2n plus 1, is roughly like 2n plus a little of n. So you get a general, for large n, this cuts it down to 2n, okay? Now these graphs, when we teach students about factorials and how fast they grow, okay, wait until you see double factorials. So double factorial, it's, the graphs grow fairly fast. So for n equals 5, this has 945 vertices and it's 20 regular. And we tried very hard with, actually Zhao Quang Tan tried, I kind of just encouraged him to try harder, to color this graph. And he could find a coloring with 7 colors. Ferdinand Ehringer tried his hand, also could find a 7 coloring very quickly. And then he decided that he had better things to do. And he said, Sebi, I'm not going to do this calculation anymore. And then we contacted Gordon Royal. And initially the coloring was tricky to find by computer, but Gordon Royal is a magician, and he could find the coloring for MK10 or 6 coloring. And then later on, he found the coloring for MK12, a 7 coloring. So you see MK12 has 10,000 vertices and is 30 regular. So this gives us the upper bounds that were conjectured by the authors of the paper in 2009. Now, when you look a little bit at the structure, so this is also observed before, like you can find this kind of argument in Nathan Lindsay papers. We basically, this graph has a very nice equitable partition, and it's a partition into what we call types. So we think of our identity perfect matching to be the 0 plus 0 minus, 1 plus 1 minus, 2 plus 2 minus. So here we're going to label the vertices from 0 to n minus 1, each of them with a plus and minus. And then when you put another perfect matching in, so the identity perfect matching is the red one. When you put a blue perfect matching in, that's going to create a 2 regular graph with the red one. And that will give you the type. So the type is basically you have a union of even cycles, and you take the lengths of those cycles, you divide them by 2, and that will give you a partition of n. And so the one on the left has a type 3 because you have a cycle of length 6, so you divide by 2, you get 3. And here you get the 1 and the 2, and you write it in the kind of partition way of decreasing, writing decreasing. Now, the other thing that will give us some information is what is called a label. So each perfect matching, we associate a label. And the way we do it is you start at 0 plus, you use a blue edge. There's exactly one blue edge. And then you use the identity edge, the red edge, and then you write down the vertex that you see. So that's 1 minus here. And then you continue, you go from 1 minus, you take a blue edge, you took the identity, and you get a 2 plus. And that's the same thing here. Here you get nothing, but then you do a blue edge with the red edge, and you get a 2 plus. So we have a label and we have the type, and the partitions into the types are gonna give us an equitable partition. And this is an example of an equitable partition for MK10. So this is the one that has type 1,5. This is identity perfect matching, and then you have 2, 1, 3, and all these other ones. So you can, it's fairly easy to see how how you have edges between these various types and so on. So that's a kind of a partition for this big graph on 945 vertices. Okay. Now you can go crazy. You can go to MK12 and you have a partition into more blobs, and you kind of see from the picture maybe already what's going on. That the one at the end, it's the one that's doing a Hamilton cycle with the identity perfect matching. So that's this can be proved. Like you have the same thing here at the end, and yeah, you can actually do the numbers and so on with all these blobs and stuff. And you can actually prove that the last subconstituent, when you look at the vertices, so this graph will have diameter, diameter n minus 1. If you look at the vertices at distance n minus 1 from this identity perfect matching, the one with this type n, they induce a subgraph isomorphic to something that I haven't defined, what it calls Sine reversal graph SRn minus 1. So this Sine reversal graph SRk is, in some sense, it's related to these burnt pancakes and pancake graphs. So again, the vertices are like the burnt pancake graph. There are sign permutations, so you get k factorial permutation, and each entry has a plus or minus sign. So you have 2 to the k times k factorial. And now, when you have an adjacency, you can flip not just prefixes, you can flip any consecutive entries. They could start in the middle. And you can also, that's another thing that it's, you can flip one entry. So you can just, for example, here I write I less than or equal to j. So I could equal j. And in that situation, you have an adjacency if in the position I, which is the same as j, you just flip the sign of that entry. Okay. So you can prove, that's what we do in the paper. We prove that the vertices at the end, they give you this sign reversal graph. And it's actually, you go into another rabbit hole, like, okay, what about this sign reversal graph? I'll tell you in a second why, this kind of could help us potentially for the flip graph. But for example, when n equals 2, the graph is the cube, the 3-dimensional cube. And then we can prove, we have theoretical proof that for 3 and 4, the chromatic number is 4, and I think the same thing for 5. And then you have an upper bound of 5 when n equals 6. So we don't know much more about this behavior of the chromatic number of the independence number. So we didn't go much further than this. Now why? So it turns out that the sign reversal graph appears in all these parts. So if you have a connected component of MK2 induced by the vertices of type lambda 1 lambda k, then so some such components may be disconnected, but each connecting component is going to be isomorphic to the box product of some sign reversal graphs of this form, lambda 1 and so on. So this one here at the end, it's isomorphic with SR3, but you can say something about each of these components. So then it's a relatively easy upper bound to prove that the chromatic number of Mk2n is at most the chromatic number of the sign reverse of n-1 and n-2, because this chromatic number, because here, for example, at the end, you have the sign reversal of n-1, so that's where you use these colors. And here, you can color with the colors from sign reverse of n-1, and then you can alternate. So it's not a super strong bound, but it will give you the bound in this situation when n equals 4. So if you chromatic number of Mk8, this is a theoretical upper bound that you can color it with, I think 3 plus 2 or something like that. Yeah, 3 from here and 2 from here, and you get a chromatic number of at most 5. Okay. Now the sign reversal, there's also a reversal graph. So the reversal is the one in which the vertices are the permutations, and 2 of them are adjacent if one is obtained from the other by substring reversal. Now, when you do substring reversal, you cannot reverse a substring of size 1 because you're staying the same. I mean, you could potentially do it and you get the graph with a loop at each vertex, but you know, if you want to keep the graph simple, you don't do that. So this graph is has n factorial vertices. Again, it's a Cayley graph of symmetric group on n elements, and is n choose 2 regular. And you know, reversal graphs and sign reversal graph, there's a large literature in mathematical biology, and there's a lot of results that Pesner has proved and so on. And it's apparently quite useful in comparing genomes, like the distance between 2 sign permutations and so on in this metric. So Barfna and Pesner proved that the diameter of Rn equals n-1, and Chang and Tobin, in the same paper in which they did the pancake graph, they have a very nice proof showing that lambda 2 of the reversal graph is n choose 2 minus n. It's a recursive proof, very, very nice. Okay. Now we looked at the sign reversal, and if you fix a permutation, let's say 1, 2, 3 up to n, and you take all the sign permutations that have kind of their support 1 to 3 n, so it could be plus minus 1, plus minus 2, and so on. The subgraph induced by these vertices is the n-dimensional cube, because the only reverses that you can have is to reverse one element on the spot. And so you can do various equitable partitions for this graph, for the sign reversal graph. This is one of them. And you get n choose 2 as an eigenvalue. You can compute several eigenvalues of this graph. And from computation, it looked, that's clearly a mistake there. It's n less than or equal to 5. So if it's true for n greater or equal to 5, we're done. So we conjecture that the second eigenvalue of this graph is n choose 2. And of course, you can prove that is at least n choose 2 because it's in the spectrum, but proving that is less, but at least we haven't been able to do it. And the proof that Chang and Tobin did for reversal graph doesn't translate immediately to the sign reversal. So yeah, that's a conjecture, a spectral graph theory conjecture for you. Now, in terms of the flip graph, so perfect matching. So well, first about independence numbers. So for MK8, again by computer, you can calculate that it's 28. MK10. I think Gordon found the independent set of size 208. That's as much as we know. You can find an easy upper bound of 2n minus 1 double factorial divided by 3, but that's not very strong. In terms of chromatic number, we only have upper bounds. So we have not been able to prove that the chromatic number of MK10 is at least 6, or MK12 is at least 7, or the kind of harder stuff, that the chromatic number of these graphs is strictly increasing. Like if you, for example, if you can show that MK2n is obtained from 2n minus 1 disjoint copies of MK2n minus 2, adjacent kind of joined together in a nice way. So yeah, so these graphs are kind of like these Russian dolls that are one inside the other. But so clearly the chromatic number is is increasing, but proving strictly increasing. Maybe this is one of like this kind of Michelski type of construction that the chromatic number is strictly increasing, but we haven't been able to prove it combinatorially or algebraically. This is a place where all these algebraic parameters, they give a lower bound of 3 for the chromatic number. So maybe there's a, I don't know, a way to use topological methods to prove lower bounds. We haven't been able to do it. Okay, let me see, anything else? Okay, well, so that's about it about flips on graphs on perfect matchings. And I have some time, so I'll tell you another flip graph. So this is a flip graph. It's called associahedron graph. It's a flip graph on triangulation of a convex n-gon. And it's quite famous in algebraic combinatorics and so on, sometimes called Tamari lattice, Stashev polytope, so on. And so here, basically, you have the vertices, you take n greater or equal to 4. In this picture, n equals 6. So you take all a convex n-gon, and you take all the triangulations of the convex n-gon by n minus 3 non-crossing diagonals. So this is, the number of them is the Catalan number. And 2 of them are adjacent, 2 triangulations are adjacent. If you take when you take one triangulation, you take one of its diagonals, you delete it, and that creates a quadrilateral, and then you put in the other diagonal. So because you have n minus 3 diagonals in each triangulation, this is an n minus 3 regular on the Catalan number of vertices. And this can be embedded. The reason it's called Stashev polytope and so on, it has an embedding, and several authors have proved such embeddings, Hofmann, I think Lee and Lode, embedding in n minus 3 in Euclidean space. So this is for n equals 6, you can embed it in R3. And that's kind of what the picture is trying to suggest. So Sletter, Tarjan, and Thurston, they studied this graph. They have a paper in 1988, and they prove an upper bound of 2n minus 10 for the diameter. So they show that you can go from any between any 2 triangulation, you can do at most 2n minus 10 flips to transform one into the other. That's a very nice combinatorial proof. And in 2014, Purnin has a paper in Advances of Mathematics proving that that's exactly the diameter. So he actually shows that gives 2 triangulations for which you need at least 2n minus 10 steps. Now, in the same paper that I mentioned earlier, these authors, they studied the chromatic number also of this graph, and they prove an upper bound of, I think, n over 2. And they make 2 conjectures that the chromatic number should go to infinity as n goes to infinity, but it grows slowly, and they say chi is at most big O of log n. So for the second conjecture, that was proved recently by Dario, Berry, Reed, Scott, and Wood. They have a paper on Archive in which they prove chi of an is a big O of log n. I think the constant there is something like 3,000 or 4,000, something like that, log n. For the first conjecture evidence, I mean, that's the only evidence as far as I know. So the previous authors of the 2009 paper, they calculate by computer the chromatic number, which is 3 for n between 5 and 9, and then at 10 it grows to 4. And we confirm this calculation. Sage can do this type of calculation, and you can get to, but we haven't gone to chromatic number of 11, A11. So A10, so the vertices are the triangulations of a tengon, and the Catalan number is 1,430. And when you move next, you get 4,862 vertices. So these Catalan numbers, they grow roughly in steps of 4, multiplicative factor. So, I like algebraic graph theory and so on. So I'm like, okay, what does Hofmann ratio bound say? So it says that the chromatic number is at least this value. And so in this situation is at least 1 plus n minus 3 divided by lambda min of an. So I'm like, okay, is lambda min of an little of n? That would prove it, but we'll see that that's not the case. So I started studying the smallest eigenvalue of this graph. Now, to do that, what's kind of the intuition? The intuition about the smallest eigenvalue is that of a regular graph is that when it gets closer to minus the valency, your graph is bipartite. So if your graph has many triangles or odd cycles and so on, it should push up. So that's a result I have that it's not very difficult, but if you have a k-regular graph, the property that each vertex is containing at least so many cycles, so, you know, and each edge is containing at most, so R is fixed here, okay, then you can push lambda min up by some value. And there is a result like this for R equals 1 in a paper by Aharoni, Alon, and Berger in 2016, in which they study the largest eigenvalue of the Laplacian for K1K free graphs, so like claw-free graphs and so on. And if you translate that for regular graphs, it's essentially a result about smallest eigenvalue. So this kind of extends their result to larger cycles. Why did this was needed is because associahedron graph does not have triangles. It has C4s and it has C5s. So it turns out that you can prove that in AN, each vertex is in at least n roughly cycle C5, and each edge is in at most 4 cycles C5. You can prove this combinatorially with triangulation. And when you crunch these numbers, you get some kind of weird expression there as a lower bound for lambda min. Then, you know, how do you get an upper bound, and what else can you say? Well, if you fix a diagonal in this graph, you take all the triangulations that contain some fixed diagonal, and what you get an induced subgraph of the associahedron graph. Now, when you fix a diagonal, you can only flip a diagonal in the n-gon to the left or in the n-gon to the right. So that will tell you that a box product of smaller associahedron graphs is an induced subgraph of the bigger associahedron graphs. So that's how you get, and then you use Cauchy interlacing and the fact that the eigenvalues of the box product are sums of eigenvalues of the other graph. And you can prove that this limit exists, and you can, with using the values for I could go up to n equals 12, and minus 3 is 9. You can you can use this argument repeatedly, and you can get that this limit is between these two values. But I have no idea what is the exact value of this limit. So, you know, the good news, there's something about smallest eigenvalue that's interesting, but it won't give you a good lower bound for the chromatic number, because it's not going to be little o of n. Now, there's a big conjecture here about the second eigenvalue of n. And this is in a paper by, it's on David Aldo's webpage, and it's connecting with the mixing time or mixing rate of random walks on this associahedron graph, because that's also quite important for people in the Markov chain community and probability community. They're looking at generating these triangulations at random. So you want to measure precisely the mixing time of this random walk. And if you rephrase the conjecture in terms of the spectral gap, it just says the spectral gap is order of magnitude 1 over square root of n. And the upper bound is kind of, no, I'm trying to understand it. I wrote to David Aldos, and he sent me an argument that I'm trying to understand, but this is still open. Nobody knows the lower bound. So the upper bound for the spectral gap is you write lambda 2 as a maximum of some Rayleigh quotient of the Rayleigh quotient of the graph, and then you pick the right vector that will give you what you want. But the other inequality is not known. Okay, so yeah, I will stop here and I'll stop sharing my screen. Thank you very much for your attention.